sometimes it announces it, sometimes it doesn't. Okay, so now we're kind of sort of changing gears. We're going to look at a number of approaches to solving PDEs that is particularly useful for problems that are defined on an infinite or semi-infinite domain. So an infinite domain, like the entire real number line, is a spatial domain for x. And by semi-infinite domain, I mean, for instance, half the real line, like all x greater than 0. The separation of variables that we've been dealing with for some time now is applicable to initial boundary value problems where you're on a bounded interval. So now we're going to get away from that. So I'll talk about some integral transforms or really over the next few lessons. And what we'll find is that when you are dealing with a problem on a finite interval, like 0 to L, then integral transforms versus separation of variables is really two different perspectives on the same technique. But we'd like to be able to consider infinite domains as well. And that's why we're looking at this. So what is an integral transform? So the short definition is it's a mapping of one function to another that involves evaluating an integral where we have variables for both functions, the input and output, as parameters. So what we have here, our input is a function little f of t, and then we multiply this by this function k of st, which is called a kernel. And the kernel depends on t, but it also depends on this other parameter s. So now we evaluate this integral over some specified domain, interval a b, which might be infinite. And the result of this integral with respect to t is a function of the remaining parameter s. So this whole expression is a function of s, and that's called the transform. So we're saying that capital F of s is the transform of little f of t. Now we're going to, one transform that you're familiar with from your first differential equations course is the Laplace transform. So that acted on the time variable and has a function of a parameter s. We're not really going to be dealing with that in this course. We will be dealing with Fourier transforms. Okay. So the usefulness of integral transforms for solving differential equations is you obtain a simpler equation. So what you saw in F285 for using a Laplace transform to solve an ordinary differential equation is it transformed the ODE into an algebraic equation. Now, what we're going to see here is if we have a PDE in two variables, x and t, you apply a transform to the spatial variable x, and now what you have is an ODE in the remaining variable t. But that ODE depends on a parameter, it's this variable s that we see here. Okay. So really that's the idea. It's just to transform one equation into a simpler one. Now, the only time integral transforms can do that, though, is if it's possible to express the transform of a derivative in terms of a transform of the original. And what you saw when you learned about Laplace transforms is that actually happened. For example, if you're transforming second derivative of a function f of t, your transform was s squared capital F of s, where capital F is a transform of little f, and then there were some additional terms. Same is true, as we'll see with Fourier transforms, that it's fairly easy to express a transform of a derivative, particularly a second derivative, in terms of a transform of the original function. So that's what makes these kind of integral transforms useful for differential equations, that it's easy to work with derivatives. So anytime you apply a transform in some variable, one of your independent variables, It's no longer a differential equation in that variable. You still have a differential equation in any remaining variables. So that's why I'll see some examples. A PDE in two variables becomes an ODE. Once you get the equation as simple as you can, you go ahead and solve it. But then you have to go back, because when you solve your simpler equation, like your PDE becomes an ODE, once you solve that, you've not found the solution of your original problem. You've found the integral transform of your solution. So it's important that the integral transform process be reversible. If I can go from a function little f of t to a function capital F of s, and then I manipulate that somehow and get another function of s, I need to be able to go back to a function of t. That's what leads to what's called an inverse transform. And in many cases, the inverse transform is fairly straightforward, but sometimes it's not, and you have to rely on, for instance, numerical methods to try to carry out an inverse transform. So, how do you determine which transform you're going to use for a particular problem? That's dictated by the domain of a problem and also the boundary conditions. What's weird is that there's one thing, I think it's a homework problem in the textbook, where it's pretty clear from the boundary conditions which transform you should use, and for some reason they use a different one. So I'll try to recall which problem that is, so that you're not thrown off when you do it. Whatever initial condition you have, you're applying your transform to that, and then you're working with its transform and solving the simpler equation. All right. So I'm going to show you select transforms that will be of interest to us, and then I'll show you how they're used. I can't fit all of them on screen, but okay. So suppose your problem is defined on the entire real number line. So you actually don't have boundary conditions. So x is going from minus infinity to infinity. So the way you transform is using this plain Fourier transform. So what you do is you have your function little f of x, and you evaluate this integral that depends on a parameter omega, and the result is a function capital F of omega. So capital F of omega is the Fourier transform of little f of x. We also use this notation, this fancy f of little f is used to refer to the Fourier transform of little f. This notation is helpful when we have complicated functions and we want to try to, like maybe we don't have a variable associated with them. They want to refer to the transform of that function. One thing to keep in mind about the Fourier transform is different books will define the Fourier transform differently. Like there might be a different scaling factor out here. I've seen some cases where there's a factor of 2 pi in here. They're all consistent, but they're all mathematically equivalent, but it's something to be aware of so you're not thrown off by it. Now, if you have capital F of omega and you want to get back to little f of x, that's where the inverse transform comes in. And notice that the inverse Fourier transform and Fourier transform are extremely similar. Note that the inverse does not have a minus in the exponent. But we're still integrating from minus infinity to infinity, but now with respect to omega instead of with respect to x. We still have the same scaling factor on here. So if you start with little f of x, take its Fourier transform, then do its inverse transform, then you'd be back where you started. Now, suppose you have a problem that's defined on a semi-infinite domain. So x is going from 0 to infinity. That means that x equals 0 is where a boundary condition is imposed. And what kind of boundary condition dictates which integral transform you're going to use. So for instance, if you have a Differential condition, or also known as type 1, where you're specifying the value of the solution at x equals 0, then you use a Fourier Sine transform, which makes sense because when we saw separation of variables is that when you have those kind of boundary conditions, the Differential condition, then your solution is expressed as a Fourier sine series. And so this is the integral you evaluate. So you multiply by sine omega x and integrate from 0 to infinity. And then you see, if you go back, it's very similar. You get multiplied by sine omega x. You just don't have a scaling factor out front. If it is a Neumann boundary condition, so you're specifying that the partial of your solution with respect to x is equal to something at x equals 0, then you use a cosine transform. So, as before, sines are associated with different boundary conditions, cosine series is evaluated associated with Neumann boundary conditions. And you see, it's pretty much identical, you're just replacing sine and cosine. Notice the notation here, I fancy s with a subscript of s to refer to a sine transform, or with a subscript of c to refer to a cosine transform. Now the last two are on a bounded interval, x going from 0 to L. And really what's happening is, this is exactly what we obtained from separation of variables. So it really is equivalent. So it just generalizes, because we saw a lot of our examples, we were on a domain x going from 0 to 1. So what you would do is you would have your solution expressed as a Fourier sine series, coefficient times sine n pi x. And how do you get the coefficients, the Sn? You would evaluate 2 times an integral from 0 to 1 of your function times sine n pi x. So this exact same thing is just defined for a general interval from 0 to L. So it's more flexible than what we've seen. But if you were solving a problem in this kind of domain with these kind of boundary conditions by separation of variables, then this is exactly the kind of form your solution would have. And this is how you would get to coefficients. So really, it's just another perspective on the exact same technique. In this case of a bounded interval. And if it's Laplace conditions, then we have cosines. Notice how here we have this additional term, C0 over 2, as opposed where sine doesn't have that. Where C0, C1, C2, Cn, etc. are all defined using this integral formula. And the reason is, if you have, like, say, sine n pi x, and n equals 0, you just have 0, so you don't get anything. But if you have cosine n pi x, when n equals 0, you have 1. So you are going to have a non-trivial term there, and that's accounted for using this term out front. So, in a lot of our examples, we see this kind of series, but if your boundary conditions change in Neumann, don't forget that you'll have this kind of term to include too. So finding the coefficients of your function, little f, in the basis of sine functions, that's called the finite sine transform, where you evaluate this integral to get those coefficients. Then using those coefficients to construct a Fourier sine series of your function, that's called the inverse finite sine transform, and then similar for cosine. It's also common to refer to Fourier transforms on an infinite domain as continuous Fourier transforms. But if on a bounded interval as a discrete Fourier transform. And the reason for that is, here, our finite sine transform is defined on a discrete domain. So only for positive integers n, or non-negative integers in the case of cosine. Whereas the transform, for a case of an infinite domain, they give capital F of omega here, that's defined on a continuum. So that's one huge difference between integral transforms for a functions on a bounded domain versus an unbounded domain. So what I'm going to do is show you how you can use one of these transforms to solve a PDE. A really initial boundary value problem. So here we have the heat equation, same old PDE. But now it's defined on a semi-infinite domain, x greater than 0. That means we have a boundary condition at x equals 0, and here we're specifying the value of the solution on the boundary, which is it's equal to some constant a. And then we have our initial condition, we're just going to let it be 0. Notice that the boundary condition and initial condition are not compatible. So, if you ask me, what's happening at the point x equals 0, t equals 0? Well, based on the boundary condition, the value at that point should be a. Based on the initial condition, that value should be 0. That does happen, unfortunately, that the initial boundary conditions might not necessarily match up. And that actually causes problems for numerical methods for solving these kinds of problems. That mismatch can lead to some bad behavior in a computed solution. So based on the boundary condition and this semi-infinite domain, it's clear that you should use a Fourier sine transform. So the Fourier sine transform needs to be applied to the PDE and also to the initial condition to obtain a new problem that's going to be an ODE in T that depends on the parameter omega. So here's how we apply the transform. I apply to both sides. I transform du dt, and then after that I'll transform alpha squared uxx. So here's what happens when I take a Fourier sine transform of du dt. Well, the definition of a transform gives me this integral. But what I'd like to do is relate it to Fourier sine transform of just plain old u. Well, there's nothing in here that depends on t except u, and that's being differentiated with respect to t. So, and the integrals with respect to x. So that means I'm allowed to pull this differentiation operator with respect to time outside the integral. But then what's left? This is exactly the definition of a Fourier sine transform of u. So really I'm taking the time derivative of a Fourier sine transform of u, which I can write this way. So if I use capital U omega t to refer to the Fourier sine transform of little u of xt, I'm just taking this time derivative. So here we can see how we're going to get an ODE in time, because the time derivative of little u transform just becomes a time derivative of big U. Questions so far?
So you're kind of allowed to treat that partial derivative notation, the Leibniz notation, as like a constant.
Yeah, because everything else that's going on in this function is treated like a constant as far as differentiation with respect to t is concerned.
Right.
Yeah. No way to think of it is if I want to take a derivative of all this with respect to t, that differentiation would go, you differentiate under the integral sign.
Right.
And that's what we're bringing back here.
Okay.
Yeah, because the 2 over pi, the sine omega x, all follow as constants. Yes?
Okay, so with the integral transforms, I want to know if they can be proven, or we're just supposed to know them.
Under certain assumptions on the function you're transforming, it can be proven that the transform and its inverse really do work, in the sense that you take transform of little f, you get big F. You take the inverse transform of big F, and you really do get back to little f. But it does take assumptions on the behavior of the function. Because since we're integrating on a semi-infinite domain. Certainly, u must be going to 0 as x goes to infinity. So this integral has to be, the integrals in question have to all be defined. But under those circumstances, yes, it really does work. In this class, we can take it for granted that they do. But, yeah.
So we know for a fact that it's a Fourier transform, but how do we know it's a sine?
We choose that because of the type of boundary condition. Yeah, and also we only have 2 transforms that can be used of the ones we've seen on a semi-infinite domain. There's a sine transform and a cosine transform. We would use a cosine transform if this was like du dx at 0t was equal to something. Yeah, so the type of boundary condition plays a key role determining which transform should be used. So now I need to transform alpha squared uxx. There's a little bit more involved than that one. So just by the definition, this is what I get. So I'm 2 over pi times the integral of alpha squared uxx. But now what I'm going to do, again, just like before, I want to relate this to the transform of u. So first I'll pull out the alpha squared. So now I have alpha squared times the transform of just uxx. But I still need to work on this to relate to the transform of u. So what I do is I carry out integration by parts. So when I carry out integration by parts on this integral, where uxx is considered the dv, and then sine omega x is considered the u, then this is what I get. And so what happens when I examine these boundary terms? Well, certainly as I substitute x equals 0, I'm going to get 0. But what about as x goes to infinity? Well, sine just oscillates forever and ever. So we do need an assumption that this will go to 0 as x goes to infinity for this boundary term to disappear. And then this is the integral that we're left with. So now we apply integration by parts a second time. And this is a result of that. And again, we have boundary terms. And when x is 0, we're going to have 1 here, and we're going to have u of 0t. But u of 0t is known because of a boundary condition. We need to assume that as x goes to infinity, u of xt goes to 0. So the upper boundary term will disappear. Now, notice I have an omega sitting here outside this integral, but I also have an omega sitting out here. So if I put it all together, then I have this. And what we have is this integral, the 2 over pi times this integral. We recognize that as the Fourier sine transform of u. So the Fourier sine transform of uxx is minus omega squared Fourier sine transform of u, plus this boundary term, u of 0t. This is why this is the appropriate transform to use for IBVP of this type, because from a boundary condition, we know what this is, A. So we fill that in. So the transform of the entire right side of a PDE turned out to be this. So now, if I put that with the left side that's what's been transformed, this is my ODE. So my PDE in x and t became an ODE in t, where omega is a parameter. So really, I have a one parameter family of ODEs, but I can go ahead and solve those by treating omega as some variable and get a solution formula for this. The initial condition comes from taking a Fourier sine transform of the initial condition that we have, and that initial data was a 0, so we're just getting a 0. So this gives us the initial conditions for these ODEs. Any questions about how we got to this point before we solve this problem? Now we know how to solve an ODE like this. We have a solution formula for this. We saw this came up previously. Actually, for the last lesson, for non-homogeneous PDEs, we end up with non-homogeneous ODEs. And so I'm borrowing that solution formula for this. So because the initial value is 0, all we're going to have is this integral where we have e to this constant times t minus s. Whatever your source term is goes in here, ds. And this integral can be worked out. Everything we have here is a constant. Because we're integrating with respect to s. But once you work out the integral and plug in the limits, this is what you get. So this problem has now been completely solved. But that is not our solution to our IBPP. It is the Fourier sine transform of our IBPP solution. We have to go back now. We have to carry out the inverse transform. So to do that, the little u of xt is the inverse sine transform of capital U of omega t. So I go ahead and fill that in. And then I'm going to rewrite this slightly. Okay, a is a constant, so I'll just pull that out. And then I have omega here. I'm just going to move that under here. And the reason for that is I've now made this fit the formula for a known inverse transform. That this expression right here, where you have e to minus a omega squared for some constant a. It's known that the inverse sine transform of this expression, which is exactly what we have here, it's just that where little a is equal to alpha squared t, is called the complementary error function. Now, a complementary error function is defined as an indefinite integral of a Gaussian function. Now, the problem with Gaussian functions are very useful in many areas of mathematics, but it's not possible to compute an antiderivative for them. It's actually been proven. So that's why we have to settle for defining this function in terms of an integral, which would then have to be evaluated numerically. But at least using this formula, we can describe our solution to our IBPP, and this is what we get. So, as I mentioned earlier, a, the constant a in this generic formula is equal to alpha squared t. So that is what goes down here in place of a. So I just fill that in, and then I have a factor of capital A from before. So this is my solution of my initial boundary value problem. And that's the end. I'll point out that if it had been a Neumann boundary condition of something of this form, you would have used a cosine transform instead. So any questions about how this solution process was concluded? Yeah.
Where did you get the 2 times the square root of alpha squared times t?
This right here?
Yeah.
Okay, because so this expression fits this one, as long as the constant a here is equal to alpha squared t. So alpha squared t goes here, and that's where we see it down here.
And that's because we're integrating with respect to omega, right?
Yes.
The Gaussian function is like e to the negative omega squared.
Yes. Right. Yes. So here omega here are playing the same role, and the inverse sine transform of this means multiplying by sine omega x and integrating from 0 to infinity omega. Other questions? Oh, okay. So for convenience, here's something to keep in mind about Fourier sine and cosine transforms of the second derivative when you're on a semi-infinite domain like we had in this example. So this first formula is what we used in the example. So it's always whatever transform. Oh, actually, I need to fix this. It should be sine transform. Okay. Forgot the subscript. So Fourier sine transform of the second derivative is minus omega squared Fourier sine transform of the original, and then we have a boundary term. And then similarly, cosine transform of second derivative is minus omega squared Fourier cosine transform of the original function, and again a boundary term. And it's from a boundary term that you can see why we use certain transforms for certain boundary conditions. It would not make sense if your boundary condition was ux of 0t is equal to something. It would not make sense to use this because you don't know what this is in the boundary. This boundary condition isn't specifying that. And this makes sense because consider a function sine omega x. If you take the second derivative of that with respect to x, what do you get? Sine omega x again times minus omega squared. And this is just recapping what I just showed you. So based on your boundary condition, you pick which one of these you're going to use. These formulas help you transform the uxx part of your PDE. The Fourier transform of the time derivative is just a time derivative of a Fourier transform, whichever transform you're using. You solve the simplified problem you get, in this case an ODE. And then perform the inverse transform, and then you're done. Now, for convenience, I have some solution formulas that you can use. So if you have same PDE heat equation on a semi-infinite domain, and it's a Dirichlet boundary condition, you have some function of t as specified on the left boundary, and some generic initial condition. Then there's your solution, which is this is just the inverse Fourier sine transform of capital U of omega t. But we know what capital U of omega t is because when we transform this, we know what we're going to get from a previous example. We're going to get a non-homogeneous ODE that you solve. And this is what we get. I can only express in integral form because the functions phi and g are not specified here. So whatever your initial data is, phi, you take its Fourier sine transform and you get capital phi of omega, and that is what goes here. We did not have this term in the example because in the example, the initial data was 0. And then you'll have this integral to evaluate. Whatever your boundary function is, that is what goes here. In the example, this function was just a constant, so we were able to evaluate this integral fully. But I'm pointing this out because if you have a problem like this, then it's perfectly fine to jump directly to here. So everything I was showing you in the example of transforming the left side, transforming the right side, working all that out, you don't have to do that. We know that this is what the transformation solution is going to be for this type of problem. If your problem fits this situation, then depending on what you have here, try to work out this integral. Once you have this as simple as you can get it, then you dump that in here. If you can, you try to work out this integral. But as we saw in the example, sometimes that's not possible. You have to settle for something like describing it in terms of a error function, something like that. Or you can just leave it as an integral. That's one thing I want to point out, like for a test. I will state in the problem if it's fine to leave your answer in integral form. I don't want you wasting time evaluating integral that can't be evaluated in the first place. I also have the other situation covered. If the boundary condition at x equals 0 changes to a Neumann boundary condition, so du dx is specified instead, then we have u of xt brought to you by an inverse cosine transform. You'll see that the solution formulas are very similar. So here there's no omega, here we have a minus instead of a plus. Whatever boundary data you have goes in here. The integral itself is exactly the same. Your initial data plays the same role. So it's really just this factor out front is the only thing that's different for one boundary condition versus the other. And then taking inverse cosine or sine depending on the boundary condition. So I put this in as a time saver. Now, if a problem doesn't exactly fit this form, then yes, you're going to have more work to do. As an example, suppose my right side here, I have alpha squared uxx, and suppose I have another term, let's say, plus a constant times u. Then most of this would still apply. It's just that when you're transforming that part, you're going to have an additional term transform. So then when you get to your ODE right here, then you're going to have an additional term like another constant times u. So that's modifying the solution formula a little bit. So changes in the PDE end up complicating the ODE that you're solving. So, questions about what we've seen here? Or other questions about the ongoing homework problems?
I might have questions
Okay.
about the homework problem, but I don't have them, so I can't.
Oh, okay. So not yet.
No, I have to look at what I've done on it already.
Okay.
Before the.
Well, I'd have to see the work that I've done already, where I've got this.
Okay.
I remember I had a couple
Also, if people are packing it in, alright, well, we're gonna stick around in case anyone has any questions, but I'm fine with stopping recording at this point. We're gonna have to see 2 more lessons of Fourier transform type stuff, and then that'll be everything. Then you'll see everything that would go on the first test. Alrighty.